looking at finding the sums of infinite geometric series. Just quick review, we've looked at arithmetic series like we have here in red. Right, it's always a common difference, so we add 3 to each of those terms to get the next term. And if I graphed that, it would be a linear equation, and the slope on that would actually be 3 from this common difference of 3. But if I wanted to look at geometric series, right, 2 different things can happen. So here on this blue one, I have a common ratio of 3, and I multiply each term by 3, right? And just very generically, this would start here, and it would increase exponentially like that. In the next sequence, here in red, the bottom one in red, I have another geometric series, but its common ratio, or R value, is 1/3. Right? So each time, or 1/2, sorry, each time I multiply by 1/2. And it's important that we stick with that concept of multiplication. We don't want to say divide by 2. We want to stick with multiplication, so times 1/2 each to get from term to term. And that would look more like this, right? It would be exponential as well, but as my x values increased, my y value, or my output, would get closer and closer to 0. Kind of from a previous chapter, we would have an asymptote there at 0. So looking today at calculating sums of infinite sequences, we have to have a special condition in place for that to even be possible. So looking here, an infinite series that has a finite sum is called convergent. And I think of little kids' sports when I think of convergent. It doesn't matter if it's basketball, football, soccer, wherever the ball is, that's where all the little kids run to. They all converge to the ball. And we saw in that previous graph on the intro that in order for a series to be convergent and have a infinite sum, the R value, the absolute value of the common ratio, has to be less than 1. So to put that in more simple terms, your R value has to be a proper fraction, either positive or negative, or it has to be a positive or negative decimal that starts off with 0 point and then continue on from there. That is the only time you can find a sum of an infinite series. So that would be the graph from the intro that looked like this. Okay, it doesn't have to necessarily approach 0, but it has to approach something. For the other situation, an infinite series that does not have a finite sum is called divergent. Okay, like a flight might have to divert and go somewhere else, go away from their intended target. Divergent series, it continues up or down towards either negative or positive infinity. So if your R value here is an improper fraction, why I wrote the I twice, improper fraction, or any other value that is 1 or bigger, you will have a divergent. That sequence and series is divergent. So putting that into practice then, we need to use this formula. It's simpler than our previous formulas. The sum of an infinite geometric series is equal to the first term divided by 1 minus r. And again, that has to be, in this case, when the absolute value of r is less than 1. So it's a proper fraction, positive or negative, like negative 4/5, positive 2/3, or some sort of decimal, positive or negative, that starts with 0 point something. If it is not that case, then there is no sum. So we are going to look at a couple of examples here. So you use the calculator. Right, so for number 1, we have a first term of 729, a second term of 243. So I'm going to use the calculator to calculate my r value, second term divided by first term. So I have an r value here of 1/3. Okay? So then I can use that formula. The sum is a1 divided by 1 minus r. So for example 1 here, I would take my first term, the 729, and I would divide it by 1 minus 1/3. Now this gets tricky to type into our graphing calculator. 729 divided by, you could do 1 minus 1/3 in parentheses. You may be better to just mental math this part and do 729 divided by, and then 1 minus 1/3 would be 2/3. With the TI-83s, we just have to be careful to put that in parentheses, put that fraction in parentheses. If you're working on a TI-84, you can set that fraction up. If you're working in Desmos, you can set that fraction up much more easily, in which case I'd probably just use the original equation. But we have a solution here of 1093.5. Right, so we have to pay attention to our r value. Another situation that comes up frequently is we get a negative r value, and then when you set up your a1 over 1 minus r, right, you'd have to pay attention here to put that negative. You would have the subtracting a negative. And again, if you put that in the calculator properly, it will take care of the double negative, making addition. But that's something to look out for. The second example here, I have to calculate my r value. So second term divided by first term, and I get 5/2. And before I even calculate that, that's an improper fraction, right? So that is going to be an r value that has an absolute value greater than or equal to 1. And if I calculate that, 5 divided by 2, I get 2.5, and that is definitely greater than or equal to 1. So this one is divergent, and that is all the work there is to do on number 2, because it is divergent. I cannot find the infinite sum. The other thing I wanted to talk about on today's lesson is rewriting, repeating decimals as a fraction. And there's some, if you're into math, some neat algebra we can do to change any repeating decimal into a fraction. So if I had a simple fraction like, or simple decimal like 4/10, right, I know with place value that becomes 4/10. I can then reduce that into 2/5. With the repeating decimal, I don't have that ability. But what I can do is use some algebra to rewrite this. So I'm going to start off by saying x, any variable, is equal to 0.18. And what I want to do is turn x, make x equal to a fraction. So given the whole concept of algebra, doing the same thing to both sides to maintain that balance, right? I am going to multiply both sides by 10 to a power, and I'm going to pick the power based on how many values are getting repeated in my repeating decimal. So here I have 2 repeating values, so I am going to multiply both sides by 10 to the second power, which is really 100. Okay, so this would become 100x equals, and then this would also be 100, which is going to scoot the decimal over 2 places. So that's going to become 18 point, right? Another 1/8 repeating is going to fill its spot, right? The 1/8s continue on here forever. And as I said at the beginning of this example, the repeating part is what makes it hard for me to turn this into a fraction. I know from my first statement that I wrote in red that the 1/8, the 0.18 repeating is equal to x. So what I'm going to do is I am going to subtract 0.18 repeating from both sides. But on the right side, I am going to call it 0.18 repeating. On the left side, I am going to call it x, right? Because those two things are the same. So I'm going to subtract x from the left side. Those two are interchangeable because I started off with this statement here, right here, that x and 0.18 repeating are the same thing. So 100x minus an x is 99x. And then over here, 18.18 repeating minus 0.18 repeating is 18. And then I just have some basic algebra left to get x by itself. So this would be x equals 18 over 99. And then I would need to do any reducing. I see that they're both divisible by 9. So that would be equal to 2 over 11. Now, I know that's a lot. There are easier ways, right? But I wanted you to understand why some of this works. So if I have 0.177 and all of that repeats, what I can do is I count the repeating digits. There are 3 of them. And I take the repeating and I make it the numerator. And then the denominator is 3 9s because there are 3 repeating places. And I can see in my calculator that those two would be the same. 177 divided by 999. And I see the 177 repeating. I can even go a step easier than that. If I want to turn 0.74 repeating into a fraction, I can simply just have my calculator do the work. Now it's important that I fill up the 7/4 repeating with at least one line of the repeating. And then under the math tool, tool number 1 is the, hey, make this a fraction tool. And so then I can hit enter. And it will do any reducing that is necessary. So for the first example, the 1/8 repeating, yes, we know that is 18 over 99, but it will even reduce that down for us into the 2/11ths. So that is your lesson for today. Good luck on your assignment, and let me know if you have any questions.